Welcome to Advanced Java Programming at Portland State University. In this screencast, we're going to learn about one of the more advanced features of the Java programming language, something called inner classes. And we're also going to look into how classes are loaded internally by the JVM, and also an API called the Reflection API that allows you to do some pretty advanced things at runtime. And we'll see how this then forms the sort of underlying implementation of technologies like the JUnit framework. We'll also finish with a discussion of something called resources, which allow you to dynamically at runtime determine the value of certain strings. And this can be used for localization, translating your application into various languages. So the whole idea behind inner classes is that it allows you to declare one class inside another class. And this is most interesting when you have a particular class or set of behaviors that's really only pertinent to one place. We'll see some examples later. And again, we'll look at Reflection, which is an API that provides information about classes, such as information about their names and their methods, allows you to invoke methods very dynamically at runtime. Inner classes are important and interesting. They're often used in GUI programming for providing things like a very little inlined algorithm for your code. The Reflection API, also something called class loading, provide the foundation for technologies like JavaBeans, remote method invocation, and like I said, also the JUnit implementation. So sometimes you have classes that have a very limited use. For instance, one class is only ever used by one other class, or maybe a class is only instantiated once. Instead of having to have sort of a top-level class that's in its own .java file, you can declare a class inside another class. These are called inner classes. So for instance, you can have inner classes, you can have inner interfaces. Also, the JavaUtil map interface declares an inner interface named entry. And we've touched on this before. An entry is basically an object that represents each key value pair in a map. Right? Map has that method called entry set that returns a set of map.entry. Now, this map.entry is an inner interface of JavaUtil map, and so a fully qualified name of that inner interface is java.util.map.entry. If you go and look for the class file of an inner class, its name is a little special. It's something like java/util/map$entry.class. So if you see class files that have a $sign in the middle of them, that means that they're an inner class. That's just the way the JavaC compiler outputs them. So syntactically, here's how an inner interface is declared. If you go look at the source code for the map interface, it looks something like this. You've got all of your methods on map here. And then, smack in the middle of your declaration of your map interface is the entry interface. So it's just another public interface entry with its methods declared inside there. So really, that's the syntax. You have a declaration of a class or an interface inside another class or interface. So here's how inner classes and inner interfaces are referenced in source code. Here we have a method called printMap that takes a map of objects to objects and prints it out to something. We saw something very similar to this in the core API lecture. We iterate over the contents of the entry set of the map, which gives us these key value pairs. And so when you call getKey on a map.entry of object to object, you get the object key and the object value. So really it's nothing that special. You just reference it as map.entry. Now there are some interesting properties of inner classes. Inner classes may not have static members unless they're final. So really it means static fields. This is just the way the language works. So basically if you're going to have a static field for an inner class, it's got to be a constant. Now, inner classes themselves may be marked as static. Inner classes have an implicit reference. So an instance of an inner class has an implicit reference to an instance of its outer class, unless it's marked as static. So if it's marked as static, it means that there's no reference between the instance of the inner class and the instance of the outer class. And this is okay. Sometimes you want to be able to create an instance of an inner class without having to first create an instance of its outer class. So if it's marked as static, you don't have that reference. which means that you can't have that you don't have that an instance of the inner class doesn't have a can't reference a instance field or an instance method of its outer class. We'll see some more examples of this, and we'll come back to it in a little bit. So you can declare that you have a class inside another class, but sometimes you only need a class once. So for instance, you have just a very particular piece of functionality, and you just want to implement that in one place. Why bother having all of the boilerplate of a class declaration? Why do you have to say public class? Can you do something more simpler? And the answer is yes. You can declare a class you can declare a class to be inlined into the middle of a method. So you're sitting there writing a method, and then maybe you need a class just for one place. You can create something called an anonymous inner class. We'll see an example of what an anonymous inner class looks like in a moment, but a couple of notes here. An anonymous inner class can work with variables in the method in which it's declared, but those methods have to be final. So an anonymous inner class can reference variables. It can also reference fields and methods of the class in which it's declared. And but in some cases, you might need to disambiguate between a variable and a field that might have the same name. You have to use a notation like the outer.this. So outer is the name of the class in which the anonymous inner class is declared, and say so it would be like I don't know appointment.this dot whatever method you want to call. The names of the class file for an anonymous inner class has a $sign in it, but since the class itself has no name, it has names like $1. So we'll see that we'll have an outer class called find class files. It has an anonymous inner class whose name is simply $1 for the first anonymous inner class in find class files. And these anonymous inner classes are really useful when doing event handlers in GUI programming. We'll be seeing this in a later discussion. But oftentimes when you want to say, hey, here's what happens when I click a button, or okay, as I'm typing my text, do this. The way this is implemented or expressed in Java is as interfaces that have particular methods like on button clicked or on keystroke type things like that. You want to create like one little specific piece of code that just does one simple thing. You're not going to reuse that code or rather, it's unlikely that you will reuse that code in a bunch of places. So why bother having like a sort of a first class, for lack of a better term, just have an anonymous inner class. Okay, what am I talking about here? Here's an example. You may recall when we learned about doing file I/O, we saw a couple of interfaces called file name filter and file filter. And we wrote a little program that started in a directory and recursively found all of the files whose names ended in .java. And we used a file name filter to basically provide the logic for determining whether or not a file has a name that ends in .java. Similarly, we used a file filter to find all of the directories within another directory so that you could recurse. And that code was spread out over 3 files. There was sort of like, there was the implementation of file name filter, there was the implementation of file filter, and then there was the main class that drove that all. But if you go back and look at that source code, the implementation of the 2 interfaces, you had a lot of boilerplate in there, right? Really all you needed to do was implement an accept method, and it's got a 1-line implementation, something like, name ends with .java. But yet you had to have, you needed to have the class in its own .java file. You needed to declare that it was a class. There was just a lot of overhead there for something that really only had one little use. And it turns out we never really reused that class. Well, here at the code that we're looking at right here, we have a program that does something very similar. It finds .class files within a directory, but it uses anonymous inner classes to provide the implementation of the file name filter and the file filter. So we're going to take a walk through this code. The syntax is a little different, but once you get used to it, I think you'll find that anonymous inner classes are really quite useful. Here we have our outer class, find class files. And it has one method. It's a static method called find files. And so it starts in a directory, and it'll recurse. It'll print out all the .class files in that directory, and it'll recurse into subdirectories. Okay, so here is the chunk of code, this class files, that finds all of the files in this directory whose name ends in .class. And how does it do it? Well, it uses the list files method on Java I/O file, like the program from the Core API lecture did. But what it passes it is the following. It says new file name filter, paren, and then a code block. And what this new file name filter does is it creates an anonymous implementation of the file name filter. So an anonymous inner class that implements the file name filter interface. And because it implements file name filter, it has to provide an accept method that takes a file and a string. And so that's the declaration of this method right here. And the implementation of the method is simply return name.ends in suffix. Here again, we have an anonymous inner class that implements the file name filter interface, and the implementation of the accept method is simply return name.ends with suffix. Now, suffix here is a variable within the find files method. So this anonymous inner class refers to a variable from the method in which it's declared, and this is okay as long as the value of the variable is final. Now, I won't go into all of the details here, but if you decompile, so if you go out and you find the class file for this find class files $1, which is the class file for this anonymous inner class, and if you look at the constructor of that object, you'll find that the anonymous inner class, this implementation of file name filter, actually takes an instance, is passed in, the suffix here is passed in to the constructor of the file name filter. And so underneath the covers, that's how the suffix is passed in. It's assigned to a field in the anonymous inner class, and that's how the accept method is able to reference essentially reference the value .class, and because it's final, we don't need to worry about it changing before the accept method is actually invoked. Anyway, you can read up on it on the internet. We can talk about it in class. It's kind of a neat thing. Okay, so here again, what we've done in 5 lines of nicely formatted code is provide an implementation of file name filter. And again, this implementation of file name filter is very specific to the find class files class. If your application reused this logic of being able to find .class files many times, then it would make more sense to put this implementation of file name filter into a class of its own with a given name. But in this case, it's not. So this little block of code here finds all of the files whose name ends with .class. So we will go and iterate over that and print it out. We should probably use an enhanced for loop here, but we're using the old style, probably because it's an old slide. Then what we need to do is we need to find all of the directories within this other directory. And so how do we do that? Well, we use a file name filter, and here again we're going to use an anonymous implementation, an anonymous class that implements the file name filter interface. It provides an accept method, who's implemented simply as, okay, well, this file.is directory. That will find all of the subdirectories, and will iterate over them and print them out. What isn't shown on the slide is that there's a main method here that reads the command line, takes arg0, and creates a file from it, and then calls find files. So what took us 3 classes spread over 3 files in the Core API lecture is now covered in one file in several fewer lines. And you can imagine as you have larger and larger programs, this syntax really helps you out. Now, coming in Java 8, purportedly, is an even easier syntax for doing things like this, something called lambdas, and these are Lambda functions from functional programming. I don't have any content prepared on it right now, but after Java 8 is released, we'll be talking about that. Okay, as we learned on the first day, Java source code, a class, Java source code for a class, is compiled down into something called a class file, which contains, well, at the time we were talking about how it contains these bytecodes that for the methods that are executed, but it also contains a description of the class itself, what its methods are, so their names, their parameter types, their return types, etc., and its fields. It's basically all of the information that that the JVM needs to know about a class. And so, as we've seen, these classes reside on a file system someplace. They reside in jar files. You can download them from over the web. You can really read them from any place. And the way this works is through a mechanism called class loading. And so class loading in Java is the process by which the bytecode, the class file, is brought into the JVM. And so when the class is loaded, the bytecode is read, is parsed, is validated to make sure that you're doing valid things. And this provides some amount of safety and protection to make sure that the code that you're getting from, well, who knows where, isn't trying to do something illegal, like execute an illegal an unknown bytecode, or trying to do something unsafe, like messing with memory, which probably isn't even possible. But more importantly, on top of all that very low-level validation, class loaders allow you to restrict certain operations, such as can it read your home directory? Can a particular class go out and connect to a remote machine over the internet, based on its origin? So you can say things like, listen, I'm willing to trust code that comes from the JDK itself fully. Yeah, it's like, hey, I'm running the platform, I'm going to trust it. But code that comes from Dave, for instance, well, okay, I'll let it do some computation, I'll let it, print out some output to standard out, but no, I'm not going to let that code read from my home directory or write to my home directory, for instance. And this whole, all of this enforcement happens because of the class loading mechanism. So when does class loading happen? Well, classes are loaded dynamically in Java, meaning the first time they're used. So even though you've got a jar file with 10,000 classes in it, you don't load classes until you need them. So for instance, a class won't be loaded until the first time that you instantiate a class, or when you reference one of its static fields. So basically, instead of loading all possible classes at the initialization of the VM, they're loaded dynamically. And this, of course, saves on time and memory, but it also means that if you have a part of your application, maybe your application starts up and there's certain parts of it that aren't accessed for, minutes or hours, it'll mean you'll have to do a little bit of work, sort of on demand. Class loaders are all descend from a class called JavaLang class loader. And so a class loader is an object that is responsible for reading a class file and turning it into something that the VM can use. Class loaders are referenced implicitly during normal JVM operations. So you're executing a method and you create you go to create an instance of a class. Maybe it's your appointment class or appointment book class, and it's not until that point where the VM actually goes out and tries to find the class file for that class and then load it. And all of that happen. You can also explicitly load a class into a JVM by calling load class. Now, load class takes the name of a class, so a string, fully qualified name of a class, and will load it. And if it can't find it, it'll throw an exception accordingly. Class loaders can be chained together. You can have one class loader that will delegate off to another class loader before attempting to load a class. And well, I think I'll show you in a couple slides that there's this sort of hierarchy between class loaders. And class loaders can load classes from different locations. And so the whole idea is that you've got a class loader that, oh, I know how to download classes over the internet, but before I try to go find a class like JavaLang string, I'll go off and delegate to the class loader that knows how to load it from the JRE itself, the runtime environment itself. So every JVM has at least 3 class loaders. There's something called the boot class loader, which here again loads those classes from the JRE. things like Java Lang Object and Java Lang String and Java IO File. Right? All those guys get loaded by what's called the boot class loader. And oddly enough, there really isn't a class loader object that you use here. It's they're just the null class loader. So if you're sort of going up the parent hierarchy, when you get to null, well, that means that the class is loaded by this very internal boot class loader. And classes that are loaded from the boot class loader are basically trusted to do everything. So a class like JavaNet socket is trusted to make sockets. It's trusted to make sockets. There's no additional security checks there. There's another class loader called the extension class loader that will load third-party classes, meaning classes that aren't part of the JRE. And they're loaded from a location underneath the JRE's JRE libext. But in terms, they're given the same security permissions, the same abilities as boot classes. So this is basically you saying, hey, listen, these third-party libraries, I trust them as if they were built into the JRE itself. And this is useful. Maybe you've got some special XML parsing library, or you've got some special image generation library that that you vetted and that you trust fully, and so you put it in JRE libext. So the classes that you put on the class path with like the -cp option or setting the class path environment variable or whatever, those are loaded by something called the system class loader. So this is another instance of class loader. Unless you explicitly configure security, these guys will be trusted implicitly. And this class loader object is obtained by calling the getSystemClassLoader method of class loader. So these are the three class loaders that are built in to the JVM. Stuff for loading the core JRE classes like Java Lang Object. You can define extension classes, and then the stuff that you put on the command line and just any old invocation of the JVM, that's in the system class loader. As I said, you can have class loaders chained together. There's also a class hierarchy of class loaders that provide different behavior. So at the very root is Java Lang class loader, and it's the thing that's responsible for essentially translating those bytecodes into classes that the JVM understands. But then there's a subclass of class loader called secure class loader, which allows you to configure the capabilities, what classes loaded from that class loader are capable of. And here again, this allows you to say that you trust some classes to do more operations than other classes. And then there's a subclass of that called URL class loader that will load classes from a URL, or actually from an array of URLs. And recall URLs, of course, can be locations out on the internet or whatever, but you can also have like a file URL for the local file system. So you can also subclass these class loaders, these class loader classes that are part of the JDK to have your own class loaders. So here's an example of I call it the logging class loader that will simply print out the name of all of the classes that are loaded by this particular class loader. So it subclasses URL class loader, and so the constructor for logging class loader needs to invoke its superclasses constructor, and it passes an array of URLs from which it loads classes, and then its parent class loader. So I can understand why it's a little confusing. There is the class hierarchy of class loaders, but then there's also this parent-child delegating relationship. So this basically says that when this logging class loader goes to load a class of a given name, and so load class is a method that is inherited from class loader, it's going to override this method to first print out that yes, it's loading a class with a given name, and then it's going to call super.load class to do the real work of it, right? So it'll just call it super method, and so the superclass is implementation of load class. And what that implementation is going to do is first delegate off to the parent class loader, see if the parent class loader can load it, and if not, it'll go through the URLs that you provided to the superclass and try to load it from each one of those URLs. Here in the main method, there are two arguments. The first argument is the URL from which you load, and actually it's a file. It's going to be a local It's going to be a file URL. So it's the file from which you load the class and then the name of the class to load. And so what do we do? Well, in order to create our logging class loader, we need two things. We need an array of URLs, and so we just call toURL on the file, and then put it inside an array. The logging class loader needs a parent class loader. In this case, it's just going to be the system class loader, what's there on the class path. And then we'll create our logging class loader and tell it to load a given class. Now, while working with all this code, several things can go wrong. When you call file.url, you might have a malformed URL exception, and so we'll print out there. And also, if we attempt to load a class that doesn't exist, we'll get a class not found exception. So let's take a minute and run this program and see what it looks like. Okay, so the first thing that we need to do is we need to, so we're here in the examples code, and first we need to run the logging class loader, the main of the logging class loader class. So the class path for the JVM here is target/classes for the examples. So that'll help. That will tell the JVM to run the main method of logging class loader. Then we need to give it the location of the class that the logging class loader loads, which is going to be off in the family jar. And then we'll give it the name of the class to load. Don't worry if you find this a little bit confusing. We're getting really meta in this lecture, meaning that we're dealing with classes not in source code, but sort of all at runtime. Right, and I'll come back to this point several times. So we're going to run first the logging class loader class, and so we need to tell the JVM, hey, load that class from this target/classes. And then as arguments to the main method to logging class loader, we're going to give it the location of a jar file to load from and a class to load from that jar file. Okay, and so it printed out three things. It first printed out that it was loading edu_pdx_cs410j family person, and then as part of loading the person class, it also loaded the serializable interface and the object interface. Kind of interesting. Let's give it some other examples. What happens if we try to load something like Java util tree set? Nope, it just loads that. Probably because it's already loaded. I wonder if it's loaded everything else about that. How about something like Java NetSocket? Nope, not so interesting. Well, unfortunately, off the top of my head, I can't think of a good example of a class that hasn't already been loaded that has a deep hierarchy. Because what I wanted to point out, and maybe we can just talk about it up here, in order to load person, we also had to load other classes. Okay, well here's an example of this family tree GUI class, which is off in that in the jar file. It had to load several classes, including the UI, family tree panel, and then just the JPanel itself. I guess the point here is that when you load one class, it can also cause other classes to be loaded. Things like interfaces that it implements, its superclasses, and maybe even its fields. Actually, probably not its fields. Anyway. Just one more thing that I wanted to show you. If we give it a non-existent class, foo.bar, it tells you it tried to load it, but then found that it couldn't. And here again, that class not found exception was thrown by the class loader when it failed to load the class. Okay, and I think that's a good stopping point. Thanks for watching Advanced Java Programming at Portland State University.